A very good afternoon and welcome to our afternoon lesson. We are still on motion and we want to look at the very last aspect of linear motion, which we call the motion graphs. Motion graphs. And motion graphs is actually the graphical representation of the variation of distance, displacement, speed, velocity, and acceleration in terms or with time. Now, we have been able to look at all these aspects of linear motion, and we have been able to see how they interact and how forces can be able to alter them in or within a certain duration. Now, within a certain duration. Therefore, when we want now to represent these alterations in graphical form, we compare each one of these and we plot them against time just to find out how the motion of a body varies with time. And that representation is what we refer to as graphical representation of linear motion, or simply the motion graphs. Now, we will start with distance, time graphs. Distance, time graphs. Now, they show how distance covered by a body, they show how distance covered by a body varies with time. How the distance that has been covered by a body varies with time. Now, when a body is in motion, it could be accelerating, it could be moving with a uniform velocity, it could be decelerating, and all those can be represented graphically. Now, let us start with a stationary body. And a stationary body is simply a body at rest. And when we say that a body is at rest, then it means as time goes by, the body does not change in position. In other words, it covers zero distance. The body is at rest. Therefore, it covers zero distance though time passes on. And we would like to show that kind of motion. We would like to show that kind of motion in graphical terms. And here we have our distance in meters. Here we have time in seconds. Now, it is good, before we even look at how the graph is going to look like, let us consider the gradient. Let us consider the gradient of this graph. The gradient of this graph is given by change in y over change in x is going to give us a gradient. On our y-axis, here we have plotted distance. Therefore, when we say we look at change in y, we actually look at change in distance. Therefore, change in distance and the time taken, change in distance over time taken. And if we go back to the terms that we defined at the beginning of this chapter, we see that now this particular formula will give us velocity. That velocity is distance over time taken. So in other words, I'm saying that if you plot a motion graph of distance against time, the gradient of this graph is supposed to give you velocity of the body. Therefore, in our graph here, we want to show a body at rest. And when a body is at rest, V is equal to 0. Therefore, time, we cannot be able to stop time, though the distance is not changing. So this graph is going to be a straight line which is parallel to the x-axis. That shows that distance of this body does not change though time passes on. Again, it is worth noting down that the gradient of distance time graphs, the gradient of distance time graphs gives the velocity, of the body. That the gradient of distance time graphs always gives the velocity of the body. Now, let us look at a second graph and probably sketch it. And probably we can sketch it. Number 2 is a body moving with uniform speed. And if a body is moving with uniform speed, again we have seen that these graphs, their gradient gives us the speed or the velocity. Therefore, it means that the gradient of the graph should be constant. It should be constant. In other words, we are saying an equal distance. An equal distance should be covered at equal time intervals. At equal time intervals, the body covers equal distance, and therefore the graph of this particular body will be a straight line through the origin. Should be a straight line through the origin. Here again, we remember to show that we have plotted our distance in meters against time in seconds. Now, the gradient which is given by change in y over change in x should be constant. Should be constant. And this one shows that at equal intervals of time, this body covers equal distance. We could have a graph of a body moving with non-uniform speed. This means the speed could be increasing or again the speed could also be decreasing. Now we can show this graphically, and this means that at equal intervals of time, this body covers a distance that is not equal. Now, let us start with a body moving with an increasing speed. A body moving with increasing speed, and we can sketch that. We can sketch that. And the graph is actually a curve and the gradient of the curve should increase with time. The gradient of the curve should increase, so that if you take the gradient at a point, say A, and then another point at B, the body should have appreciated in the value of gradient, which translates to an increase in speed. How about a body moving with decreasing speed? This means that the distance covered at equal intervals of time is not equal or decreases with time. Again, if we sketch this is distance in meters, this is time in seconds. We should have a graph which is actually a curve whose gradient decreases with time. Now, let us look at speed time graphs. Speed time. Speed time graphs. And again, we could try to interpret these graphs in general, and the gradient of these graphs, which you are going to call again M, is given by change in y over the subsequent change in x. On our y-axis, we have plotted speed, and on the x-axis, we have our time factor. And looking at that formula, speed divided by time should give us the rate of change of speed, or what we call acceleration. That if we look at speed time graphs, it's a plot of speed against time on the x-axis. Therefore, if we want to obtain the gradient of these graphs, we will consider the change in y over the change in x, and bearing in mind that on the y-axis we have plotted speed, on the x-axis we have time. Therefore, we are looking at the change in speed, and that one we are dividing by the time taken, and that one gives us the rate of change of speed, or what we call acceleration. Now, we look at the different graphs that we could have, and number one is that of a stationary body. Or what we call a body at rest. A stationary body, or what we call a body at rest. And when a body is at rest, v is 0. Though time is going to pass by, but velocity of a body that is stationary is actually 0. Therefore, if we could have a plot of that, where this one is the speed now in meters per second, and this one is the time taken in seconds. Now, we cannot draw anything on that particular grid because we have 0 velocity. So our graph is going to remain like that. Now, we could consider a body moving with uniform speed. Uniform speed. A body moving with uniform speed, and this means that velocity does not change with time. Velocity does not change with time, which means that our plot is going to be that of a graph that has 0 gradient, therefore it should be a straight line that is actually parallel to the x-axis. Now, we could also have another type of motion where a body moves with constant acceleration. And again, we have said that acceleration in our case is given by the gradient of our graph, and therefore this is to mean that gradient will be constant. This can be interpreted to mean that at regular intervals of time, the speed of this body is actually increasing at the same rate. It is not it is actually increasing at a constant rate, and therefore the motion is going to be plotted as a straight line through the origin, so that the gradient does not change. It is actually constant, or in other words, you could say the gradient does not change. How about a body that is decelerating uniformly? A body that is decelerating uniformly is also supposed to have a graph This graph is going to have a uniform gradient, though in this case the speed is decreasing. Therefore, the gradient of this graph is supposed to be negative. If we plot this on a grid, this is our speed in meters per second. This is our time in seconds. Now our graph is going to exhibit a negative gradient that is actually uniform. A negative gradient that is uniform, to show that the body's the velocity of the body decreases uniformly. Uniform decrease in the velocity of the body. Let us look at questions to do with motion graphs. Questions to do with motion graphs. Look at questions to do with motion graphs. And question number one requires us to sketch the following. Motion graphs. We sketch the following motion graphs. Number one is the distance time graph for a body falling from a height to the ground. Distance time graph for a body falling from a height to the ground. We are talking about distance time graph. Again, we agreed that when a body is falling from a height, it is acted upon by the force of gravity, which makes it accelerate uniformly downwards. So in other words, this graph should be a motion graph for a body that is accelerating uniformly. That when a body falls from a height to the ground, the force of gravity has an effect on that body, and therefore it is going to accelerate at a constant rate, and we can only end up with a graph of a body that is accelerating uniformly. Let us try and sketch that. It's distance time. And a distance time graph for a body that is accelerating is a curve to show that the speed is varying uniformly. Now, let us look at part 2 of the question. Part 2 is a distance time graph for a body thrown up. Distance time graph for a body that is thrown up. Again, here we have also vertical motion, where now a body is moving upwards. Therefore, the gravitational acceleration though uniform is negative. It is negative and uniform. Actually negative and uniform, and therefore the sketch will be a curve whose gradient is decreasing. We'll also look at part C. Displacement time graph for a body thrown up, and the displacement follow vertically. You know that for a vertically projected body, displacement is 0 when it comes back to its point of projection, to its point of projection. And therefore, the displacement time graph will be something like that. Now we look at question number 2. And on this question, example 2, we are supposed to interpolate the following graphs. We should interpolate the following graphs. A, we should interpolate the following graphs. A, we have a distance time graph distance time graph that is actually a curve, and this curve shows that the gradient is increasing at regular time intervals. At regular time intervals, the gradient is actually increasing. Therefore, the gradient of this graph, remember, tells us something about the speed of this body. Now that is a distance time graph. The gradient gives us the speed of this particular body. And if the gradient is increasing at regular intervals of time, then we could interpolate the gradient, the graph, to mean that the body is moving with increasing speed. The body is actually moving with increasing speed. Now, we could also have another graph to interpret. which is actually a velocity time graph. Again, the gradient is non-uniform and it is actually increasing. But again, we remember that the gradient of this graph should give us the gradient gives the acceleration of this particular body. Therefore, the fact that the gradient of this graph is increasing shows that the body accelerates non-uniformly. It actually accelerates non-uniformly now that the gradient is increasing at regular intervals of time. Let us consider another graph. We try and interpret it. It's also a velocity time graph. Velocity time graph. It's actually a straight line through the origin, and again we have another straight line with negative gradient. Now, first thing to note, it's a velocity time graph. Therefore, the gradient gives acceleration. Now, the first bit of the graph shows a positive gradient that is very uniform. The gradient of this line at any particular point is actually the same. Therefore, the same case will apply to the gradient of the second part of the graph, but this time the gradient will be negative. And now it means that the negative part of the graph shows reduction in velocity actually to 0. Therefore, we could say that the body starts from rest. The body starts from rest. Why from rest? Because we have started from 0. And when a body has 0 velocity, then we say the body is stationary or actually at rest. So the body starts from rest, accelerates uniformly to a velocity v. Here, this is the point we are calling v. We cannot commit ourselves to give it a figure because the graph does not give us a figure. Then it decelerates to 0 or to a stop. That initially the body was at rest, it accelerated and attained a maximum velocity we are calling v, and again the velocity reduced to 0 with time. Now the final graph that we are going to consider is actually a displacement time graph. Displacement time graph which is a straight line through the origin, and this graph, for this graph the gradient gives the variation or the change of displacement and the time taken. Therefore, the gradient shows us the velocity of the body. Now, looking at the graph, it is a straight line through the origin, and therefore it means that the gradient is actually constant. The gradient is very constant, and this implies uniform velocity. Uniform velocity, that shows uniform velocity. Now, let us look at area under the graph. Area under the graph. Area under the graph. And on area under the graph, we look at area under the velocity time graph. We look at the area under a velocity time graph, and we shall have to show it diagrammatically. Let us assume that on the y-axis we have plotted velocity. Now on the x-axis we have the time taken. Then we have a straight line and now we are interested in this area, the area under the graph. Now, area under the graph, we have a triangle whose height is V. This is the origin, and then we have time taken. Therefore, this area becomes a half VT, becomes a half VT, and the product of velocity and time, we recall that Vt is equal to displacement, and therefore we could be justified to say that the area under the velocity time graph this one gives us displacement. It's actually equal to displacement. Let us take an example. We could take an example. A car starts from rest and attains a velocity of 72 kilometers per hour in 10 seconds, with which it travels for the next 5 seconds before decelerating to a stop in 6 seconds. Now, the first part of the question requires us to sketch that motion graph. Let us make an attempt at sketching it. You sketch a velocity time graph for the motion. And so we first change 72 kilometers per hour, we change them to meters per second, we multiply by 1000, then divide by 3600, and that should give us 20 meters per second. So from rest, now we are required to attain a velocity of 20 meters per second. And then this should be achieved in 10 seconds. So we attain a velocity of 20 in 10 seconds. Move with it that is 20. We should move with it for the next 5 seconds, and then slow down to a stop in the next 6. In the next 6 seconds. Part 2 of the question requires us to get the distance covered by the car. Distance covered and we have said this one is the same as area under the graph. And I want to take it to be a trapezium. We get the area, which will be a half of 5 plus 21, and this one we multiply by 20, which is going to give us a half of 26 multiplied by 20, which is the same as 260 meters. Then the last part requires us to get the acceleration at each point. Here, acceleration is equal to velocity change. You divide by the time taken. For the first part, let us call this part A, this is B, and this is C. The velocity changes from 0 to 20. Therefore, for part OA, acceleration will be given by 20 minus 0 over time taken, which is 10 meters per second. And this one gives us 2 meters per second squared. On part AB, change in velocity is 0, which means that acceleration is equally 0. And the last bit of the journey, which is BC, velocity changes from 20 to 0 in 6 seconds. Therefore, change in velocity we divide by the time taken. This is going to give us 0 minus 20. These are meters per second, and we are required to divide by 6 seconds. And this will give us negative 20 divided by 6, which should give us negative 3.33 meters per second squared, which means that the body is actually decelerating at that rate. Now, that is all about motion. When next we meet, we talk about Newton's law of motion. Thank you.